Good morning. This is Dr. Praveen Kumar Tirlangi. I'm an associate professor, Department of Infectious Diseases in Kasturba Medical College, Manipal. So many of my colleagues and my friends, they keep on asking me to teach antibiotics. So antibiotics is not a rocket science. It is like more like a mathematics. So if you understand the principles, you'll be able to choose the right antibiotic for any of your patient. So we are going to focus on gram-negative infections in subsequent few lectures. So we will do this in 4 chapters. Today we are going to discuss about the mechanisms of drug resistance in gram-negative bacteria. This will be followed by sessions on basics of antibiotics, the side effects, the indications, management of drug-resistant gram-negative infections with the primary focus on carbapenem-resistant infections. We also discuss about less common and uncommon gram-negative infections like spice group of organisms, Serratia, Proteus, Providentia, Morganella, Citrobacter and Enterobacter, Stenotrophomonas, Burkholderia sheepacia complex, and Ralstonia, few other. So this is chapter 1. In this chapter, we'll be focusing on the structure of gram-negative bacilli, beta-lactam antibiotics, the enzymes of gram-negative bacteria to break these beta-lactam antibiotics, beta-lactamases, and the molecules which we are using to inhibit these beta-lactamases, beta-lactamase inhibitors, Porin channels, efflux pumps, and interpretation of culture susceptibility report. So when we are using antibiotics, we want to always know how to escalate. If you started the patient on some antibiotic, and if the patient is not responding to the treatment, you want to escalate the spectrum of the antibiotics. So this is the antibiotic ladder. So these are the common antibiotics we keep using in our practice: ceftriaxone, ceftazidime, and cefoperazone. These are third generation cephalosporins. Then you have cefepime, which we call it as fourth generation cephalosporins. Then you have antibiotics with beta-lactamase inhibitors: sulbactam, tazobactam, clavulanic acid. These are beta-lactamase inhibitors. Then you have carbapenems, and if your bug is resistant to carbapenems, we are left with few options. These are not beta-lactam antibiotics. These are most of the times these antibiotics are something which are from other group of antibiotics. So among the beta-lactamase and beta-lactam antibiotics, if your bug is resistant to third generation cephalosporins, that is ceftriaxone, ceftazidime, and cefoperazone, but susceptible to fourth generation cephalosporin like cefepime, then the mechanism of resistance is most likely AMP-C beta-lactamase. So resistant to third generation cephalosporin, susceptible to fourth generation cephalosporins like cefepime. And if your bug is resistant to third generation cephalosporin but susceptible to BL-BLI inhibitors like BL-BLI combination like ceftriaxone sulbactam or piperacillin tazobactam. So then mechanism of resistance is going to be extended spectrum beta-lactamase. So it will be resistant to both third and fourth generation cephalosporin but susceptible to a BL-BLI combination, right? And if your bug is producing some enzymes that breaks the carbapenems like meropenem, imipenem, and ertapenem, then the bug will be carbapenemase uh, producing bug. So one of the most important thing when we are talking about antibiotics is not to use terms like MDR and XDR. Previously, people used to call MDR bacteria when only one or two classes of drugs are active against that bacteria. But with advent of many new antibiotics, this classification is redundant. So now if you are calling something as MDR, that doesn't mean anything. So we have to be very specific, whether it is a AMC producer or ESBL or is it a carbapenemase producer. Carbapenem resistance. There are other mechanisms of resistance also, like efflux pumps and Porin channels. So basically, what we are discussing here is beta-lactamase mediated resistance, right? So we know among this class of antibiotics, again you can see Pseudomonas is little different because Pseudomonas is a gram-negative bacteria with very less number of Porin channels. Porin channels are important for the antibiotic to enter into the bacterial cell wall. So if you don't have Porin channels, and if the Porin channels are very small, as in the case of Pseudomonas aeruginosa, it is likely to be intrinsically resistant to many of the antibiotics available. For example, among third generation cephalosporins, ceftazidime cephalosporin is effective against Pseudomonas, but ceftriaxone is not. Fourth generation cephalosporin like cefepime are active. Among PLBLI combination, again, cephalosporin, sulbactam, piperacillin, tazobactam are active against Pseudomonas, but not amoxicillin, clavulanic acid. Even among carbapenems, altepinem doesn't have any activity against Pseudomonas because it's a large molecule, doesn't enter into the Pseudomonas porin channels, whereas meropenem and imipenem are effective. So this is the jargon which we have to understand. We have to understand what is MC beta lactamases, what is extended spectrum beta lactamase, and what is carbapenemase. So let us move to the other part, the structure of cell wall. So many of the times, many of my students even have confusion between lipopolysaccharides and peptidoglycan layer somehow. So peptidoglycan layer is a very specific layer which is in between outer membrane and inner membrane, right? So this is peptidoglycan layer. So peptidoglycan layer is very important because it maintains the cell wall integrity. So if you damage the peptidoglycan layer, the cell wall will lysis. So that is the reason why many of the beta-lactam antibiotics they target peptidoglycan layer. So we keep seeing antibiotics binding to three different penicillin binding proteins, penicillin binding protein 1, 2 and 3 in the peptidoglycan layer. So if the antibiotic will come here, bind to penicillin binding protein, that will lyse the peptidoglycan layer, leading to eventually bacterial cell wall lysis. Now penicillin binding proteins which we are saying are not building blocks, they are actually enzymes required for the synthesis of peptidoglycan layer. So this is one of the major target of beta-lactam antibiotics. By inhibiting peptidoglycan layer, we are doing a cell wall lysis. Besides that, there are some other targets like protein synthesis inhibitors. So the antibiotic will go and bind to ribosomes in the 50th subunit or 30th subunit, and thereby inhibiting the protein synthesis. Examples like macrolide antibiotics, for that matter, even tetracyclines inhibit the protein synthesis. Some of the antibiotics they go directly bind to the DNA, for example, fluoroquinolones, and thereby inhibiting the bacterial replication. Some of the antibiotics like cotrimoxazole are antifolate antibiotics, so they will again decrease the synthesis of DNA. So these are the other targets. So in such case, we discussed about the penicillin binding protein once. So penicillin binding proteins, three important penicillin binding proteins are there: PBP1, PBP2, and PBP3. Most of the antibiotics they are directed against PBP1. If you inhibit PBP1, that will lead to a rapid cell lysis. Whereas PBP2 is very important for a gram-negative bacteria to maintain a bacilliform shape. So if you inhibit PBP2, the bacteria will become spiroplast. And PBP3 is again important for the bacterial replication. So if you are inhibiting replication, the bacteria keeps on elongating and it will turn into filamentous form. So some of the antibiotics like carbapenems, which are very effective, they bind to multiple penicillin binding proteins, thereby causing rapid lysis of the bacteria. Now we are also exploiting this PBP proteins, like for example a newer antibiotic called cefepime zidibactam. Zidibactam has a very high binding ability to PBP2, so it will make it as a spiroblast. And once the bacteria is becoming spiroblast, the mechanism like porin channels or efflux pumps are becoming less effective. At the same time, cefepime, which binds to PBP1 and PBP3, is making the bacteria into filamentous form. So if you are making the bacteria into filamentous form, at the same time if you are blocking PBP2, it will lead to a cell wall lysis. So cefepime zidibactam component in cefepime zidibactam is decreasing the MIC. So this is the newer mechanism. We call it as beta-lactam enhancer drug, zidibactam. So this is one mechanism. So basically you have to remember is most of the beta-lactam antibiotics they will bind to one of the PBPs. Most of the antibiotics which you use routinely they bind to PBP1. Cefepime binds to both PBP1 and PBP3. Carbapenems will bind to all the penicillin binding proteins. Imipenem has a little bit more binding to PBP2, and meropenem will have more binding to PBP1 and PBP3, right? So now, now you are trying to target the cell wall peptidoglycan layer. So the bacteria has to survive it. So it has different mechanisms to inhibit the beta-lactam antibiotics. So when the beta-lactam antibiotic is coming and trying to bind PBP, uh, the bacteria can mutate in one of these PBP, PBP1, 2 or 3. PBP2 is otherwise well conserved across the gram-negative bacteria, but bacteria can sometimes mutate, insert some mutations in PBP1 and PBP3 to become resistant. But this is a little uncommon mechanism of resistance because any mutation in penicillin binding proteins will have fitness cost for the bacteria, right? So the most common mechanism of resistance is production of beta-lactamases. So if you have a beta-lactam antibiotic coming and trying to bind to peptidoglycan layer in this periplasmic space, the bacteria will produce some enzymes from chromosome, either chromosome or from the plasmid, and these enzymes will go and break the beta lactam antibiotics. So these are called beta lactamases. So AMPC beta lactamases or extended spectrum beta lactamases or carbapinamases are these enzymes which will go and break the beta lactam antibiotic. There could be another mechanism like modification of Porin channels. Now this is very important, especially in Pseudomonas, because Pseudomonas already have very little number of Porin channels, and it doesn't really depend upon the Porin channels to take substrates from the environment. So it can really modify, especially with imipenem. We call it as OPRD. Loss of OPRD Porin channels will lead to resistance to the carbapinums. Efflux pumps are another mechanism. There are many of the antibiotics share this common mechanisms, like quinolones and carbapinums have a similar efflux pumps. So once you start someone on quinolone and if the bacteria is trying to become resistant to quinolone, it can actually become resistant to carbapinum as well. So there are variety of efflux pumps. The most recent efflux pumps, advanced efflux pumps for bacteria are called R&D efflux pumps. So these are the different mechanisms by which the bacteria will try to become resistant to antibiotics. So one of the most important mechanisms we talked about is beta-lactamases, the enzymes which are breaking beta-lactam antibiotics. Now, because there are beta-lactamases, we try to produce beta-lactamase inhibitors, right? So you give a combination of beta-lactam with beta-lactamase to bacteria, and the beta-lactamase will actually protect the actual beta-lactam to act. For example, you are giving piperacillin tazobactam, and if the bacteria is producing an ESBL, the tazobactam will take care of ESBL, and piperacillin will go and bind to a penicillin binding protein. That is the thought process. But not all beta lactamase inhibitors are similar. So uh, we have four generations of beta lactamase inhibitors. We will discuss about that. But before that, this is a AMBLUS classification. You don't have to remember the classification, but one has to understand that the class C is AMPC is nothing but AMPC beta lactamases, which we have discussed. Then we also discussed about ESBLs. So there are different types of ESBL. All ESBL enzymes are not similar. So you have TEM, SHV, and CTXM. In India, the CTXM beta lactamases are little bit important because CTXM beta lactamases can actually break the tazobactam. So there could be piperacillin tazobactam resistance because of CTXM beta lactamases. There are other beta lactamases like VB and PER, which are more produced by Pseudomonas. So these are beta lactamase inhibitors. This is AMPC beta. These are different extended spectrum beta lactamases, and this is the AMPC beta lactamase. There are some enzymes which will break carbapinums. Among class A, there is something called KPC, which is a carbapinamase, which will break the carbapinum. KPC is not a major mechanism of carbapinum resistance in India, but in Western world, most of the Klebsiella isolates they produce KPCs. Okay. Among class B, all the enzymes produced are carbapinamases. These are called metallo beta lactamases. NDM, VIM, IMP. There are many other SIM. So there are many other beta lactamases. These are the common metallo beta lactamases. So VIM and IMP are majorly produced by Pseudomonas. NDM we keep seeing commonly in E. coli Klebsiella. Now even in the isolates like Serratia or for that matter Pseudomonas acinetobacter or Enterobacter and Citrobacter also we are seeing NDM isolates. So these are the very strong carbapinamases. So once you have a bacteria producing NDM, the MICs for carbapinams will be quite high. Then we have a class D beta lactamases, of which OXA48 family is very important. It will cause carbapinum resistance. OXA48 majorly produced in E. coli and Klebsiella in India, also in Enterobacter species. But other than OXA48, there are other OXA enzymes which can also cause carbapinum resistance. These are very important mechanisms in Acinetobacter. So OXA 23, 24, 51 and 58 are the common enzymes which are produced by Acinetobacter. Most of the Acinetobacter with carbapenem resistance has OXA 23. So whatever newer beta-lactam, beta-lactamase inhibitors, they are focused towards more of a KPC and OXA 48. They won't take care of OXA 23 mediated resistance. So we need a very specific beta-lactamase inhibitor which can inhibit the resistance mediated by OXA 23, 24 and 51, 58. So these are very specific for Acinetobacter. So in Acinetobacter we have a new drug called sulbactam, durlobactam. So durlobactam is very effective against non-OXA 48 mediated carbapenem resistance, right? So to for these beta lactamases, we try to make beta lactamase inhibitors. Now there are four generations of beta lactamase inhibitors. The first generation has clavulanic acid, sulbactam, tazobactam, which we keep discussing. So in this, if you compare a beta lactamase with a seizure, beta lactamase inhibitors are different compounds which will inhibit the seizure from cutting through the beta lactam antibiotic. So first generation, we can compare first generation beta lactamase inhibitors with a cloth, and second generation beta lactamase inhibitor with a metal foil, and third generation beta lactamase inhibitors with a magnet, right? So what is happening in the first generation beta lactamase inhibitors? They are trying to bind to the scissor, that is beta lactamase, but they were also cut. So they are not actually inhibiting the beta lactamases. They are obstructing the beta lactamases by committing suicide. So we call it as suicidal beta lactamase inhibitors. So they will go and bind to the beta lactamase, but they are not able to completely inhibit beta lactamases. So they are increasing the time where the beta lactam antibiotics will have time to bind to PBP1. Okay, so you can compare it with the cloth. So these are called suicidal beta lactamase inhibitors. The problem with suicidal beta lactamase inhibitors is if you have a very high inoculum load, so if the bacterial load is very high, then it is possible that it will produce so much of beta lactamases, and eventually it will go and cut the beta lactam component of your antibiotic before binding into PBP proteins, right? So the among the first generation beta lactamase inhibitors, there is a new beta lactamase inhibitor called N-metazobactam. It is also a first generation beta lactamase inhibitor, but it is more efficient, especially with the CTXM beta lactamases which we are discussing about. So the binding is more tight, and even so it is more effective compared to the other beta first generation beta lactamase inhibitors like tazobactam or clavulanic acid. Coming to the second generation beta lactamase inhibitors like avibactam, relibactam and durlobactam, these are non-suicidal beta lactamase inhibitors. So we can compare it with metal foil. So the beta lactamase will try to cut through it, but the beta lactamase is not able to. So they disengage, but again the beta lactamase when go and try to bind to the beta lactam antibiotic, the beta lactamase inhibitors will come again into the active moiety of the beta lactamase. So it is kind of engaging and disengaging and not allowing the beta lactamase inhibitors to break the beta lactam ring. What about third generation beta lactamase inhibitors? They are boronic acid derivatives. So avibactam and tanibobactam. They will actually mimic an intermediate compound of beta lactam. So it will look like that the molecule is attracting beta lactamases, and it will go and bind to the beta lactamase, and it will not disengage. Even if it disengages, it will be very slow. So they are very effective molecules. So you can compare it with magnets. So the magnet will attract the scissor, but once scissor tries to cut the magnet, it will not be able to cut the magnet. At the same time, it is tightly bound to the magnet. So bebobactam, tanibobactam, in the name you can see that borbactam, that indicates the boronic acid derivatives. Whereas second generation beta lactamase inhibitors, we call them as DBOs, diaza bicyclooctane compounds. So you can compare the second generation with a metal foil and third generation with a magnet. Fourth generation we discussed about zidibactam. These are actually not beta lactamase inhibitors. They are beta lactam enhancers, and we already discussed about the mechanism by which they act. So you can kind of compare the first generation beta lactamase inhibitors with a cloth, and metazobactam is probably a thicker version of this cloth. Second generation beta lactamase inhibitors, they are DBOs. You can compare that with a metal foil. Third generation beta lactamase inhibitors, you can compare with a magnet. So these are beta lactamases, but in Pseudomonas we already have discussed that it has very less number of porin channels and the porin channels are very small. That is the reason why Pseudomonas is intrinsically resistant to many of the antibiotics. Among these porin channels, one specific porin channel which we have to remember is OPRD, which causes selectively imipenem resistance. So there are number of porin channels even in Klebsiella and E. coli. You can see OMP, FC, and D, and Pseudomonas has very less number of porin channels. And Pseudomonas doesn't really depend upon porin channels to take the substrate from the environment. So the loss of porin channels won't affect the fitness of the Pseudomonas. So it is one of the easier mechanism for the Pseudomonas to develop resistance to uh, many of the antibiotics. Right. So this is important. If you are seeing a Pseudomonas isolate, there are three mechanisms of resistance are there. One is production of beta lactamases. So in Pseudomonas produces a lot of AMPC, where we call it as PDC, Pseudomonas derived cephalosporinosis. So if Pseudomonas is having very high production of PDC, it will break the piperacillin tazobactam. So there can be piperacillin tazobactam resistance. If the Pseudomonas loses OPRD channels, these are very important for imipenem entry. So if there is a loss of OPRD, then it will become resistant to imipenem. Among the carbapenems, like meropenem is very prone to efflux pumps. We call it as MEXAB OPRM in Pseudomonas. So efflux pumps are one of the reason for selective resistance to meropenem. So loss of porin channels is causing imipenem resistance, efflux pumps are causing meropenem resistance, and PDCs are causing resistance to beta lactamase inhibitors, right? So if you can see these four types of cultures in Pseudomonas. This is interesting because sometimes the culture reports looks like little abnormal, right? So in the first isolate, you can see it is piperacillin tazobactam susceptible, but imipenem resistant. On a gross view, it looks like how can it be carbapenem resistant but susceptible to a BLBLI, right? So, but again, you can explain this mechanism of resistance by loss of OPRD channels, because OPRD is very important for the entry of imipenem. Again, the second isolate, you can see it is piperacillin tazobactam susceptible, but then it is susceptible to imipenem but resistant to meropenem. So there is a discordance between different carbapenems. Clinically, it is very important. Sometimes you might see culture reports not reporting meropenem, just giving imipenem susceptible, and many of the times the clinicians assume that if it is imipenem susceptible, it will be meropenem susceptible also. But that is not right. You have to call the lab and ask whether the isolate is susceptible to meropenem or not. So this mechanism of resistance can be explained by efflux pumps, because meropenem is more prone to efflux pumps mediated resistance. The third isolate, again, you are seeing that it is piperacillin tazobactam resistance. So definitely it is a PDC mediated resistance. But then you have a imipenem resistance and meropenem susceptibility. So this is the bacteria which is producing both PDC, and there is a loss of OPRD. So porin channel mutation along with enzymes. In the fourth scenario, it is resistant to piperacillin tazobactam but susceptible to imipenem and meropenem. So no efflux pumps, no OPRD mutations. So this is because of PDC. That's because of the enzymes produced by Pseudomonas. So these are different culture reports which we find in Pseudomonas aeruginosa. What about Klebsiella and E. coli? Do you see this kind of discordance in Klebsiella and E. coli? You see in the case of ertapenem. We will not get a ertapenem susceptibility report in Pseudomonas because it is intrinsically resistant to Pseudomonas. So ertapenem is one of the good carbapenem antibiotic which you can give once in a day. It's a highly protein binding, long half-life. So once a day dosing is very easy in the case of ertapenem, except in the cases of hypoalbuminemia, because it's a highly protein binding drug. If you are giving it in a patients with hypoalbuminemia, it can clear faster, and that can lead to resistance to failure of the treatment. Besides that, if the patient is stable and if you want to give a carbapenem antibiotic once daily, ertapenem is a great option. The problem here is, again, you should not assume that a meropenem susceptibility and imipenem susceptibility is equivalent of ertapenem susceptibility. You have to call the lab and ask whether the bug is ertapenem susceptible or not. This is because, again, the porin channels. So some of the porin channels like OPM K36 in the case of Klebsiella can lead to ertapenem resistance but susceptible to meropenem and imipenem. Ertapenem is relatively larger molecule compared to meropenem and imipenem, and important porin channels are required for its entry into the bacterial cell bus. So loss of OMPK36 in Klebsiella can lead to ertapenem resistance but still maintaining the susceptibility to meropenem and imipenem. What about efflux pumps? There are variety of class of efflux pumps. So R&D efflux pumps are very broad efflux pumps with a variety of antibiotics can be thrown out of the bacterial cell through R&D efflux pumps. This is one of the major mechanism of resistance. For example, in Acinetobacter baumannii you have ADC, ABC. So these efflux pumps will discuss more about it. Tigecycline is a substrate for this ADA, ABC efflux pump. And again, you have a MexAB, OPRM in Pseudomonas aeruginosa, which is where meropenem is more of a substrate for these MexAB, OPRM efflux pumps, right? So the thing is, some of these efflux pumps are shared between quinolones and carbapenems, you know, and that is the reason why we try to avoid quinolone antibiotics in the treatment of anything, any clinical condition for that matter, because there is a risk of subsequent development of carbapenem resistance, especially in patients who are immunocompromised, whom you know that readmissions are going to happen. Try to avoid quinolone antibiotics if you can, but many of the times we are not left with many options because quinolones are one of the antibiotics with great oral bioavailability. So if you really want to switch it to oral, quinolones are good antibiotics, but again they have a field effect. If the bacteria is trying to become resistant to quinolone, it can become resistant to many other antibiotics. Then again you have a ABC, ATP binding cassette efflux pumps in E. coli with McAB, TOL-C. Okay, you can have other major facilitator superfamily like NORA and FARC for the different mechanisms of resistance. So these are different efflux pumps. You don't have to remember all these efflux pumps, but I think R&D is important to remember. R&D is resistance, nodulation, and division. So these efflux pumps will keep coming in subsequent lectures. So this is what we are discussing, discordance between TZ-cycline and minocycline susceptibility. In clinical setting, especially with Acinetobacter, many times you see your bug is susceptible to minocycline and resistant to TZ-cycline, and vice versa. Sometimes it will be susceptible to TZ-cycline and resistant to minocycline. So, among the tetracyclines, you have doxycycline, then minocycline, then TZ-cycline, then you have some newer glycycyclines like eravacycline or madacycline. Tigecycline is a glycycycline. So if you compare meropenem and tigecycline, tigecycline is a larger molecule, minocycline is a smaller molecule, penetrates minocycline in fact penetrates cell better than tigecycline. So previous tetracyclines like doxycycline were very prone to efflux pumps like TET A and TET B efflux pumps. So then we made minocycline. Minocycline is somewhat resistant to these efflux pumps, can be affected by TET B efflux pump, but tigecycline is really resistant to TET A and TET B efflux pumps. But again, with the R&D efflux pumps like ADEBC, it has more, tigecycline is a more of a substrate to ADABC compared to minocycline. So if you have a ADABC efflux pumps, it will be tigecycline resistant, minocycline susceptible. But whereas if you have a TET B efflux pump, it will be minocycline resistant and tigecycline susceptible. Then you have something called TETX. TETX is not an efflux pump. Many of the times people combine TET-A, TET-A, TET-B and TETX. TETX is a mechanism of enzymatic degradation, and if you have a bacteria producing TETX, it will be class resistant. So even other glycocyclines like omadacycline and iravacycline will not act if there is a TETX mediated resistance. So let us go through few of the culture reports. So this is a urine culture showing E. coli. It is ceftriaxone resistant, cefepime resistant. So it is resistant to both third and fourth generation cephalosporin, susceptible to beta-lactamase inhibitor. So likely mechanism of resistance is extended spectrum beta-lactamases. Now there are many extended spectrum beta-lactamases. It could be because of anything. It could be because of Timori, or it could be because of SHV, or it could be because of some of the CTX. So we cannot really say which enzyme is it unless you do a genotypic testing. In India, E. coli, I think SHV is more predominant, but we cannot make a conclusion. India is a big country, and every center will have a different mechanisms of resistance. But one has to remember that if there are CTX and beta lactamases, sometimes even piperacillin tazobactam can be resistant, despite of it being ESBL. For example, this case, this is resistant to both third and fourth generation cephalosporin, but resistant to piperacillin tazobactam also. So probably the bug is producing ESBL, and that ESBL is CTX. What about Pseudomonas? This is resistant to ceftazidime, so resistant to third generation cephalosporin, susceptible to fourth generation cephalosporin. So this is a AMC mediated resistance, right? So this is an AMC producer. What about this Acinetobacter? It looks like it is resistant to all the antibiotics. So many of the times people try to say that we have a case of pan drug resistant Pseudomonas. There is nothing called pan drug resistant. It depends upon number of antibiotics you are really testing. So you don't have a report of colistin, polymyxin, minocycline, cefidericol, or tetracycline here. So you cannot call it as pan drug resistant. So it is basically carbapinum resistant Acinetobacter, and if it is an enzyme mediated carbapenem resistance, in Acinetobacter the most common enzymes produced in India are OXA23 along with OXA24, 51 or 58. 50% of Indian isolates they also produce NDM. So sulbactam, durlobactam, which is very effective against OXA23, OXA24, 51, 58, which are Acinetobacter enzymes, might not be effective if the isolate is producing NDM. So India, that is the problem. Even if you have a sulbactam, durlobactam, it might not be effective against 50% of Acinetobacter isolates. What about this Pseudomonas? This is resistant to third generation cephalosporin and fourth generation cephalosporin, but it is susceptible to a BL-BLI. So basically it is a ESBL. So this is the ESBL mechanism, and then you have resistance to imipenem but susceptibility to meropenem. So this is OPRD mediated mechanism. So this bug is producing both ESBL and OPRD. There is a loss of OPRD channel. What about this? Resistant to third generation cephalosporin, resistant to fourth generation cephalosporin, susceptible to a beta-lactamase inhibitor. So this is definitely a ESBL again, but here it is resistant to meropenem but susceptible to imipenem. So more likely it's an efflux pumps mediated mechanism. So this is a ESBL plus efflux pump MEX-AB PRM. Again, look at this. This is a Klebsiella isolate. I think it's a mistake. It should be ertapenem. Klebsiella isolate, which is uh, uh, resistant to third and fourth generation cephalosporin, susceptible to BL-BLI. So it is definitely ESBL. But then you don't expect efflux pumps and porin mediated channel mediated resistance except for in ertapenem. So in ertapenem, if there is a loss of loss of pouring channels, then there can be differential susceptibility to ertapenem and imipenem. So ertapenem resistant and imipenem susceptible. So this could be because of the pouring channel mediator resistance. This can also be because of carbapenemase production, because ertapenem is more likely to be destroyed by carbapinamases even the smaller amounts. So sometimes if you have ertapenem resistant and meropenem susceptibility, so then probably you have to check for carbapinamases because your treatment might fail, even though it is a less common mechanism of resistance. 80 to 90% it's because of the